Hello everyone, once again I would like to welcome all the viewers to this online class that is conducted especially for the class 10 students. Today we are going to do circles which we are going to continue from last class. So let us begin. Last class we have proven the theorem which states that the tangent to a circle and the radius through the point of contact, they are perpendicular to each other. And the converse of that statement is also true, which we are going to do today. That is, if a line is drawn through the endpoint of a radius of a circle and perpendicular to it, then it is a tangent to the circle. Today we are going to do this theorem, which is the converse of that theorem 1. Now, we are given a circle, so first of all we will draw a circle and a tangent or a line which is drawn. Suppose this is the center of the circle and this is the radius, then this line is drawn through the endpoint of this radius in such a way that this line is perpendicular to this radius. Then the statement of the theorem says that this line is a tangent to this circle. That is what we are going to do. So let us write down the proof. So we are given a circle of center, let's say O. So let us name this center of circle to be O and this endpoint of this radius to be P, and let this tangent be A, B. So we are given this circle, say of center O, and this line AB, which is drawn through this endpoint of this radius in such a way that this line is perpendicular to this radius. So a line AB passing through P such that AB is perpendicular to the radius. This is what is given in the question or in the statement. Now what we have to prove is that this line is a tangent to this circle. That is to show that AB is a tangent to the circle. So in order to show that AB is a tangent to this circle, we must show that this line is touching this circle at exactly one point. Now this line is touching this circle at this point P. We have to show that there is no more common point between this line and this circle other than this point P. So let us take now any point of this line. So let us take this point Q, which is other than P, anywhere on this line, and we will join this OQ meeting this circle at this point R. Now let us take any point Q on AB which is different from P. So this is the construction that we are taking in order to show that this AB is a tangent to this circle. Then any point on AB other than Q cannot intersect this circle, so that this line AB will become a tangent. So now again we will use what we have done for the previous theorem, as this OP, this line OP is perpendicular to this line. So of all the line segments joining O to any point on AB, OP will be the shortest line segment. So that's what we are going to use here. So as OP is perpendicular to AB, so OP is the shortest line segment of all the line segments joining O and any point on AB. So this OP is the shortest line segment and Q is any point on OB. So as OP is perpendicular to OB, so OP in particular will be shorter than OQ. So that's why here, so therefore OP is shorter than OQ, or we can write this as, or OQ is greater than OP. So as you can see from here, OQ is greater than OP, and OP is the radius of the circle. So from here we can say that as OQ is greater than the radius of the circle, so Q must lie outside the circle. So from here, that is Q lies outside the circle. So if it lies outside the circle, which means that it is not on the circle. So when we have taken this point Q anywhere on this line AB other than P, we have shown that Q is outside the circle. And if you take any other point also anywhere on this line AB, you will get that that point will always lie outside the circle. So from this line AB, P is the only common point between this line and this circle. So by definition of a tangent, we can conclude that AB is a tangent to this circle. So let us write that down. So therefore P is the only common point between AB and the circle. So hence by definition we have AB is a tangent to the circle. So this is the proof of this theorem. Now we will use these two theorems, which we are going to do some exercise now. Now let us do this one problem, which states that O is the center of a circle of radius 8 centimeters. The tangent at a point A on the circle cuts a line through O at a point B such that AB is 15 cm. We have to find OB. Now first of all, let us draw the diagram. So we are given a circle of radius 8 centimeters. So this is the center O, and this radius, which is 8 centimeters. Now a tangent at a point A on the circle. Suppose the point A is on the circle, so let us take this point A to be here. Now let us draw a tangent. So this tangent will cut a line through O in such a way that will cut a line through O at that point B in such a way that AB will be 15 cm. So this will be the line through O. So if you draw this line, you have to draw in such a way that when this tangent cuts this line, this length AB will be 15 centimeters. So this is what is given in the question. Now we are asked to find OB. So the solution. So the solution, by that first theorem that we have done, that theorem states that the tangent and the radius through the point of contact, they are perpendicular to each other. So this is the tangent to the circle at this point A, and this is the radius through this point A, which is the point of contact. So by that theorem, we have this angle to be 90 degrees. So let us write that. So since the tangent to a circle is perpendicular to the radius through the point of contact, therefore we have that angle OAB to be 90 degrees. So we have this triangle OAB, which is a right angle triangle. So we are given, so this will be the height and this is the base, or you can call this the base or this the height. Then this side here will be the hypotenuse. So we can use Pythagoras theorem to find this side OB. So from right triangle OAB, we have OB square is equal to OA square plus AB square. We get this from Pythagoras theorem. And OA and AB, they are given in the question. So from here we can substitute. So OA is given to be 8 centimeters and AB is 15. So we can solve for OB from here. So this will be 64 plus 2 to 5. So from there we will have this OB square. If you add these two numbers, you will get 2, 8, 9. And you can work out for this one and you will get the answer to be 17 centimeters. So therefore OB is 17 centimeters. Let us do this theorem, which states that the lengths of the tangents to a circle from an external point are equal. So we have a circle and the tangents, they are drawn from an external point. So from an external point we know that only two tangents can be drawn to a circle. So let us draw these two tangents. Let us draw these two tangents. Suppose P is the external point Then this tangent, suppose it's touching the circle at this point, we call this point to be A, and this one at this point, let's say B. Then the statement of the theorem states that these tangents PA and PB, they are equal in length. That is what we have to prove. So let us call this center of the circle to be O. Now we will write down what is given to us. We are given a circle of center O, and P is the external point. PA and PB are tangents to the circle from an external point, which is P. And here we will do some construction, and we will join OA and OB, and finally we will join this OP. Then as you can see from here, this is a tangent and this OA is a radius of this circle through the point of contact. So by that first theorem that we have done, this angle will be a right angle. So similarly, angle B will be a right angle. So the construction here is we join OA, OB and OP. Now we will have a look at these two triangles, triangle OAP and triangle OBP. Just by having a look at these two triangles, we can see that they are similar, but let us see how much similar are they. As you can see, both are right triangles, and this OP is a side of this triangle, also it is a side of this triangle OAP. So from these two triangles we have, first of all, we will write down here that what we have to prove that the lengths of the tangent are equal. So we have to prove that PA is equal to PB, and from triangles OAP and triangle OBP, we have OP is equal to OP. This is a side of this triangle on top, and it's also a side of this triangle at the bottom. So it is a common side because they are both common side. And also this angle OAP is equal to angle OBP. They are both 90 degrees. So we have angle OAP is equal to angle OBP, both equal to 90 degrees. And finally, this side OA is of this triangle, which is the radius of this circle, and this side OB is a side of this triangle OBP, and it is a radius of the same circle. So they are equal, and OA is equal to OB. So they are both radius of the same circle, each radius of the circle. So from these two triangles, we have this side which is common, and then we have two angles which are 90 degrees each, and we have this also which is also equal. OA and OB, they are equal. So therefore from these equations that we have that triangle OAP is congruent to triangle OBP. By that congruence, right angle hypotenuse side. So these two triangles, they are not just similar to each other, but they are congruent to each other. So that's why they are equal in all aspects. So this PA will be equal to the corresponding side of this triangle, which is PB. So hence we have PA is equal to PB. So this is what we have to prove according to the statement. Let us do this one problem from this chapter. So here in the figure we have to find PO dash if PA is 12 cm and O dash B is 5 cm. So we have to find PO dash. So from here, if we have a look only at this circle here, the bigger one, these are the tangents to this circle from this external point. So from that theorem, these two tangents will be equal in length. So let us first write that down. Since as tangents to a circle from an external point are equal in length, so we have from that first circle we have PA will be equal to PT. And now let us look at this smaller circle. These are tangents to this circle from this same external point. So again, by that theorem, these two tangents will be equal in length. So we have PT will be equal to PB. So we have this, and PT is equal to PB. And it's given in the question that PA is 12 cm. So as PA is equal to 12 cm, so PT will be 12 cm. As PT is 12 cm, PB is equal to PT. So we have PB is 12 cm. So this, we have got this length PB to be 12 cm. And in the question, what we have to find is this distance PO dash. And again, this is a tangent to this circle, and O dash B is a radius of this circle through the point of contact. So this angle, by that first theorem, it will be 90 degrees. So again as tangent to a circle and the radius through the point of contact are perpendicular to each other. So therefore we have that angle O dash BP. Therefore angle O dash BP will be 90 degrees. So we have to find PO dash. So from this triangle O dash BP, this is a right angle triangle at B, and O dash P will be the hypotenuse. So we can use Pythagoras theorem. So from right triangle O dash BP, we have, by Pythagoras theorem, we have square of the hypotenuse will be equal to the sum of the square of the other two sides, BP or PB square. And O dash P is given to be 5 centimeters, so this will be 5 centimeters square, and PB is 12 centimeter, so 12 square. So from here, O dash P square will be 5 square with 25 plus 1 for 4, and you get this to be 169. So from here if we work out, we will get O dash P to be 13 centimeters. So we have got PO dash. So this is the end of the problem. We will stop here, and with this we have done with chapter 10. So I hope you have understood, and for the other problems I hope that you can solve using the 4 theorems that we have done. So until then, we'll see you next time. Thank you.